Thank you, Patricia, for inviting me. And I thought I will talk about something about molecular antenna, which is a concept for pre-concentrating things, molecules, basically. But I will also talk about portable and miniature sensors. How do I go forward? Oh, okay. So I don't have to talk about why molecules are important. It's you already know these things. So these are the acknowledgement. I have many students, and this is a collective work of lots of people. So outline, I'm going to talk about miniature sensors first, and then introduce the portable sensors and what the chemical sensing using MEMS, and maybe a little touch off with the standoff sensors, talk about a molecular antenna, and then another challenge is how you deliver electrical power. So I'm going to skip all these things because you already know these things, why detecting different chemicals are important. And so even this is a simple slide showing how the chemical sensor is going to operate. We have to have a sample collection, absorption on some transducer, measure the property change, readout, and display. These are the vapor from simple physics. How many molecules are there per cubic centimeter. So you can see that it is pretty small number depending upon what molecule that we are looking for. And I thought this is an interesting slide, basically showing human order threshold. This is given in parts per million, and humans are very sensitive to extremely small number of molecules, like a 10 to the power 6 molecule per cc for vanillin, while phenol is 10 to the power 14 molecules per cc, and there is a different, depending on the vapor pressure, you can have all different numbers per cc. Dogs are very good in sensing lots of these molecules because they have more than 300 million receptors compared to human, which is around 5 million receptors. Once the molecules are come to the surface, they have to adsorb on some place. So molecules are coming in parts per million, parts per billion, parts per trillion in centimeter cube per centimeter cube of air. Once it comes to the surface, there is always a pre-concentration effect happening because of the surface energy, depending upon whether it's a strong interaction or weak interaction. You can get a monolayer that will be around 10 to the power 15 molecule per square centimeter. And residence time, how long the molecules will stay on the surface, depends on the heat of absorption and the temperature. So there are many different surfaces that we can make with where we can control the surface energy. So generally metals, oxide, nitrides, and so on, they have a high surface energy, and molecules can absorb much better. So we can either through morphological manipulation or the material itself that can give us this enhanced adsorption. When the molecules come to the surface, there are four main things can happen. One, London type dispersion forces can happen, which is an induced dipole multipolar approach. Induction forces, then charge transfer, then eventually bonding between the adsorbate and the adsorbent. So mostly these are physical physisorption, where energy of adsorption is extremely small, while here in the chemisorption, adsorption energy is much stronger. So they may not desorb in the in ambient temperature. So we have to stay within this range. So when the molecules adsorb on a surface, for example, a hydrogen bond, that is around 10 to the power, approximately 10 to the power minus 11 Newton. A covalent bond will be around 10 to the power 9 minus 9 Newton, you know. So again, depending upon the interaction energy between the adsorbate and adsorbent, you can have a very large deviation in the range in the delta H between these things. So we want to stay within the physisorption area. One of the problem is that when molecules adsorb, physisorb, uh, they are not very selective, because everything will adsorb with the physisorption because low energy, either van der Waals interaction or hydrogen bonding. We can go up in energy, but then the reversibility become a very big problem. So it is not reversible. So this is a challenge. So we have to stay here, and how can we get a high selectivity? So let me introduce the sensor that I'm using, which are basically microfabricated cantilevers or bridges or some resonator. The cantilever is interesting because it will give you one more information in bending. For example, molecules adsorb on the cantilever surface, the frequency will change, and this is a Brownian motion frequency. We are not mechanically vibrating cantilever. It is undergoing Brownian motion, and you can see the shift in frequency depending on the mass, which is given by here. Dm is the adsorbed mass, m is the mass of the cantilever, df is the change in frequency, f is the frequency. In addition, if we were to restrict the molecular adsorption only to one surface by making the surface of the cantilever, both sides, chemically different. Maybe one side is inert, other side will have some kind of a self-assembled monolayer or different metal and so on. Then you have a differential stress because of the material. Solids also have what you call surface tension. We call surface energy. So difference in surface energy due to adsorption creates a torque, basically a force, a moment, and basically cantilever bend. The bending delta Z is proportional to the change in stress divided by modulus. Nu is the Poisson ratio. And this gets amplified by the length divided by T square. So this is an extremely sensitive way of detecting things. So let me give you an example. This is an old slide, but it shows exactly what is happening. So this is PETN, which is an explosive molecule. We have modified the cantilever surface with the mercaptobenzoic acid monolayer, SAM, self-assembled monolayer. This red line shows the time we are the cantilever bending, and this is the point we are injecting the PET and vapor without changing the flow rate. Initially, nitrogen is flowing through it. Then we introduce this vapor. These are acoustic peaks, and then cantilever bends. It reaches a steady state. You turn it off, and it comes back again. The blue dots that you see are the Brownian motion frequency of the cantilever, and that follows pretty well with the bending. So bending is related to adsorption energy, while the frequency is related to adsorbed mass. So this is a beautiful analytical tool. We can actually measure the energy per molecule, adsorption energy per molecule. So we have calculated it for this case is around 18 kilocal per mole or so. So another interesting advantage of cantilevers microfabricated. This is a chip of few millimeter by few millimeter. This may be 5 millimeter by 3 millimeter or so. There are 32 different piezo-resistive cantilever, all electronic readout. Then we can deposit different self-assembled monolayers on different cantilevers and look at the pattern, right? So these are the things that we developed over the years. This is the much older version. Then we made it into this version. This is a small paper clip. Then this is a quarter. And also this is a implantable type sensor with the 8 piezo-resistive cantilever behind this titanium frit with the 8-channel telemetry, works with the 2 hearing aid batteries that will go between these 2 clips. So this is again showing the same thing again. This was implanted in rat, for example. This is a rat, and we have given rat some alcohol and looking at the real time. So wirelessly, the chip is the sensor is inside the rat, subcutaneously implanted, and this transmits the data, and then the antenna picks it up, and this is the data. So this is a real-time data coming out. But now the problem that we realized that battery life is a challenge. So you have to cut open the rat again, change the battery, and keep on doing that. So I don't think rats are going to like that part. So we kind of stopped this project. So this is some of the data from this chip. Actually, there are 32 different cantilevers coated with the different polymers or self-assembled monolayers. I'm showing only 4 of them for acetone, ethanol, water, TNT, toluene, and unknown vapor. So then you can use a pattern recognition. You train them with the acetone and these pure chemicals first. Then you can use the machine learning technique to figure it out what the chemical compound is. So we can also introduce multimodal physics. That means in addition to mass and energy, you can also include infrared radiation, for example, or nanomaterials where you can have nanotubes and things like that grown on it. But the biggest challenge that I experienced is that when you functionalize the cantilevers and so on, they are miniature in size. Area of the cantilever is only 10 to the power minus 8 meters square. So it's pretty small. And if there's a little defect in the monolayer or polymer layer or antibody or something like that, that is going to affect the reproducibility. So this is a big challenge, and including even putting the gold on the cantilever that can vary depending upon the deposition condition. And that has actually Peter Gruder from McGill has demonstrated this many years ago. So this is where we thought maybe we, instead of using polymers and self-assembled monolayers, maybe we can use something else, maybe interaction of photons with molecules. So cantilever, when you make it as a bimaterial cantilever, is extremely sensitive to temperature because cantilever has an extremely small thermal mass or thermal capacitance, and it can detect 3 to 10 millikelvin at room temperature without any cooling. So this is absolutely amazing. You have such a nice thermometer that can do the small changes in temperature very accurately. These are the equation related to it. You can make it a simple equation that basically is saying that change in Young's mode, change in the coefficient of thermal expansion between two material under the change in temperature make the cantilever bend. So we deposited gold on the cantilever, silicon cantilever, and exposed it to, say, different wavelengths, say 200 nanometer to 900 nanometer. This is the cantilever bending shown here. And you can see this light actually comes from a mercury light source. And we have a monochromator. So you can see all the lines of the mercury spectrum in the light, actually. And this is not based on Beer-Lambert principle. This is a mechanical detection of the spectrum, right? So extremely beautiful, very nice Q factor here. So then we realized that we can also use IR, infrared, from say 3 micron to 14 micron, where most of the molecules have unique vibrational characteristics. And people use that for environmental monitoring around 3 to 5 micron region. 7 to 10 micron is mostly used for defense and security and industry and so on. Medical devices can be around, this 8 to 12 micron. So when molecules are adsorbed on a cantilever, physisorbed, there is no chemisorption here, no coating, just bimetallic cantilever. Molecules are physisorbed on the surface. We can excite them with these wavelengths, and they get into higher vibrational state, and they decay very fast, which is a non-radiative relaxation, causes heat in the system. And the cantilevers, since they are very sensitive thermometers, cantilever is going to bend. If the molecules are absorbing this photon, infrared photon, cantilever is going to bend. So initially we put a TNT vapor adsorbed on the cantilever. So this is a cantilever bending as a function of wavelength, say 2 to 14 micron, from a glober and a filter wheel. And you can see the spectrum of TNT. This is PETN vapor adsorbed on the cantilever. Again, you see another spectrum, and you can send two vapors, PETN and TNT, and the spectrum looks like a linear combination of TNT and PETN. So because molecular vibrations are linearly independent of each other, so you can have all kinds of vibration going on, and we will be able to separate it using some program, for example. It's also work for complex samples like a naphtha, like a kerosene, for example. And again, remember that this is a very small globar with a filter wheel, and you can see all the peaks of the naphtha. This is the ATR and FTIR data. We can comparison. Here, adsorbed molecules are around a picogram level. Here you need a much larger amount, higher amount. And you can identify all the bonds from this vibrational spectrum. You may ask the question why ATR and FTIR can resolve spectrum while we cannot. Because our slit was a little large, because the power of the light source is very small. So the slit has to be opened. So too many wavelengths are coming at the same time. So they are all kind of merged together. But if you make the slit tighter and then make the light source better, we should be able to resolve these things. So we also started doing PFAS like everybody else. So cantilever, the PFAS absorbed on it, we can measure the mass. You can shine different wavelength, 800 nanometer wave number to 1800 nanometer, and you can identify the peaks of the PFAS on the cantilever. So remember that there is no receptor here. There is no chemical interface. Molecules are physisorbed on the surface, minding their own business, and we are hitting it with the infrared photons. What about liquids? So people ask this question all the time, why not liquid? So we are encouraged by Scott Manalis, who is at MIT, who came up with the hollow channel cantilever. So we kind of changed the design a little bit, made a cantilever and made a microfluidic channel on the top of it. So this is the microfluidic channel. Total volume is 50 picoliter. And so this is the SEM picture showing the channel, basically. And this is a cut of the channel. You can see there's around 10 micron in width and 3 micron in height. So this is good for ideal for liquid sensing. Very small amount of liquid. You can measure the mass, and you can also do infrared spectrum. You can make this cantilever bimetallic, shine IR light. Then molecules get absorbed. They can also produce spectrum. So we filled it with a fumarate and glucose, and you can see this is the cantilever bending, and this is the wave number for glucose and fumarate. You can see that this is 10.5 millimolar, and this is around 5.4 millimolar to so we thought we will maybe modify inside with some peptide and trap some bacteria. So we trapped some bacteria. So bacteria are inside, and you can see the fluorescence, for example. So you can measure their what do you call the infrared spectrum, their mass, their stress, because they are there. And we can also look at the noise in the cantilever. So this is the noise in the cantilever with the bacteria inside it with the PBS buffer solution. And then we send some sugar solution. So bacteria started metabolizing this sugar. And so you can see this noise on the cantilever. The cantilever is vibrating with it. These amplitudes are extremely small, you can nanometer amplitude. Then we send ampicillin 30 minutes after exposure, you can see that they are all become very quiet. You send more sugar solution, nothing happens. All of them are dead. So this is a kinomycin. We gain bacteria plus PBS solution, bacteria plus sugar solution, kinomycin drug exposure. And unlike penicillin, ampicillin, kinomycin didn't do anything. So this way we can look at what bacteria are drug resistant and things like that. So you don't need very much. It's a 50. The volume of the liquid is only 50 picoliters. I'll skip this one. So we can do all kinds of micro and nano sensors. I'm skipping the nano sensor, which is in the other slide. So one of the problem, the Achilles heel of the micro and nano sensors is that they have a very small surface area. So if you want to detect some molecule at a very low concentration, the probability of that molecule coming and sitting on the cantilever is extremely small. Like I showed the slide earlier, how many molecules are there per cubic centimeter, right? So they're in very small concentration if you're looking at the parts per billion, parts per trillion level. So even look at the QCM. QCM is not a microsensor, but it's kind of large, 1 centimeter square. But they have a LOD limit of detection around 1 nanogram. So 1 nanogram per centimeter square they can detect. On the other hand, surface acoustic wave devices, high frequency devices, they have also nanogram, 0.2 nanogram per centimeter square, or even better. Micro cantilever, when you look at in terms of area, suddenly you can see that it is not that sensitive, right? It's a 10 nanogram per centimeter square. Even though we can detect picogram on the cantilever, per square centimeter, it's not good. Nanowire, which I didn't show the data, you can detect, this is actually taken out of a reference. They can get very small amount, 10 to the power minus 24 gram, according to this paper. But when you calculate per centimeter square, it is not that good. Or nanothermocouple, which we published a paper recently. It can say autogram level, but per centimeter square, it is pretty small. So what does it mean? When the chemical sensor is very large, it can detect molecules much better than when the sensor is very small. So generally people use pre-concentrator. This is from Professor Sean Lim. Many people make all kinds of different pre-concentrators, collect all the molecules when they are appearing at a very low concentration. I like Sean's the approach because he is using a hierarchical approach, metal foams and morphs together, and they get a very, very nice results. And basically pre-concentrate for say a couple of minutes, and then heat this material and release the adsorbed vapor. So we thought of another idea. Maybe we can have a molecular antenna, just like a regular antenna. Molecules can be adsorbed anywhere on the surface, and we can shine the infrared light, and the re-emitted radiation, we can pick it up by keeping a nano sensor at here. So it's a combination. So we kind of separated where the molecules are absorbing the sensor from the adsorption area, two different locations. That basically changed the dynamic of the whole thing. So this is the experiment. So you have a little parabolic dish, a parabolic mirror, uh, absorb the molecule on the surface. Then you hit it with we had a quantum cascade laser, so it's easy to use, which is a tunable IR radiation. We can also use the glow bar if you have filter wheel and so on. So we shine the light, and then this area exposed is much, much larger than the cantilever, and the cantilever pick up the photons, just like the way I showed it earlier. So here is the PFAS physis orb on the surface of the mirror, and you can see the MA means molecular antenna, and the FTIR is the blue one, and it kind of produces the data very clearly. And we have shown that this has if you increase the area of exposure to the radiation, you can increase the sensitivity by orders of magnitude. That's what we are showing here. We can uh, see parts per trillion level at this time. Basically, it's very hard to create parts per trillion level molecule in a standard conditions. So basically, we are depositing more and then let it dissolve, and then look at the mass dissolved as well as using another sensor, and then go back in reverse direction and look at it and say, okay, we can see parts per trillion level. You can also see DMMP, which is a methyl phosphonate, and it's a chem warfare agent, simulant. You can see nicely all the spectrum. They can also mix them together, DMMB, PFOA, all kinds of things. And the spectrum will look like a linear combination with a spectral matching technique. We can actually separate the different spectrum. What about liquid? So liquid, you can actually take a little liquid in a parabolic dish. You can spin it. It form a thin layer, because the infrared has a finite penetration depth into water, for example. So you have to have a very thin film, actually, right, to get the infrared spectrum. And that's what we are doing it here, and then use the sensor to pick it up. So you can shine the whole light all over this parabolic dish. We also showed that this also possible to use instead of a rotating uh, mirror, spherical mirror, you can also use a plain surface and thin film, and also collect the light using a lens, for example. So this is various liquid that we have done using the lens arrangement, and you can see that methanol and toluene and ethanol, all these vapors, liquids can be detected. Now comes to the thing that I didn't address. How can we address the battery challenge? Before that, let me make one more statement. So I showed two type of sensors. One, miniature sensors, where we need what do you call some kind of a chemical interface for molecular recognition. It can be self-assembled monolayers or thin polymers, and array-based approach, and you can do the what do you call the pattern recognition, AI type approach. Or the only problem there we found is that the most of the time the uniformity of the coating is not there from chip to chip, so reproducibility can be poor. So the another problem we uh, uh, encountered during the miniature sensor part was the battery. So there is a guy, Nikola Tesla, who originally proposed this idea, but he never published any paper. So we have to go and do some research to find out what he's doing, actually, what he was doing. And basically, he was looking at a standing wave. That's what we think. We don't know what his original idea was. So basically, we have been told that you need two wires for electricity transmission. That may not be completely correct statement. In the electrical engineering, the electrons will go through one wire, go to the load, come back through another wire. And what we are saying that no, electrons don't need to go home. So this is the one wire. We're going to create a standing wave, quarter standing wave. And so this side is oscillating. It's a high frequency. We converted we are using a megahertz frequency. So this is the antinode. The the amplitude is much higher, the electric field, and here is zero field. So Poynting's vector will be going back and forth or along this wire, actually. So this is the inside the lab. This is a linoleum floor, rubber buckets, wooden stick, and light bulb. This is a little metal piece. We wanted it to reflect the wave. It gives a little capacitance, send it back for impedance matching. The light bulb is coming on, as you can see it here. So this length of the wire is lambda by 4, actually. So then we made a different arrangement. This is again one wire coming in, and this is aluminum foil. This is a wooden desk. This is a 50-watt light bulb or so, and he's touching it, but nothing happens to him. And he's going to put the light bulb on it. It comes on. So electrons there's only one wire, and it's all basically wood. So it works. It also works with the linoleum floor, metal desk, another thin insulator, the Formica on it, and it comes on too. So, and it's very safe. You can touch it. You can, no problem anywhere. Let's say, so this you can buy it in Walmart. We removed the batteries from it, connected the motor using some wires to the leg, aluminum foil, is a Rubbermaid desk here, and you can get as long as they're on the one leg is touching the aluminum foil, it works. This is two of them. So two of them working together. We can also communicate them by imposing our signal on the power. So why we need this? So this is Patricia is interested in biomedical applications. So if we want to implant sensor like the one I showed you, without batteries. So battery can be worn on the hand or a belt or something, and you can put the sensor on the body or inside the body. So it doesn't have to be a human. It can be a car or a plant or anything like that, or pipeline. Or so this is Charles Van Nest. He's a professor in Tennessee now. So we connected the power to his hand. Power comes on his other hand, on his shoulder, his head, and everywhere. So you can have power delivered all over the body. Body is energized. Remember that this is a safe power. Current and voltage are out of phase in time. So E field and B field, B and E vectors are perpendicular to each other in space as well as in time, basically. They are out of phase. So whenever there is a power, there is voltage, there is no current. When there is a current, there is no voltage. until it comes inside our system. We change the phase back into the normal phase. We also did it for the ground. This is Tesla had a dream like this to power the whole world, but he couldn't do it because JP Morgan pulled the fund on him. So we found a house with a 40-meter drop in their backyard. So we went and talked to them whether we can play in their backyard, and they said fine. So we, put our single wire here, and it powered the whole their lawn. So we can just touch the, a metal piece and a coil, and the light bulb will come on. So we use only the LED, very small power, because we don't want people to worry about the bugs and the earthworms and so on like that. So we have some funding from UNICEF at this time, doing the agricultural sensors, buried all over somewhere in Tennessee, and it look for the metabolomic gases from the microbiota, and then we can transmit it back to the some source. And so this is the current outlook, and how the miniature sensors are working. And I think I'm going to stop here. Sorry about the uh, being late. So